Okay, so I'm now going to do something completely different. And at this moment it will be it will not clear unless, well, if this is the first time you see this, it should be not the first time, you should have seen it before, what the relationship is with the previous talk. And this is about anti-derivatives. By the way, this material is actually not in the volume 2 from Calc 2, but it's in volume 1 from Calc 1. So go to the website if you need to see this. I mean, I'm sure you have the link already, textbook, but you can go to the OpenStax and instead of volume 2, take volume 1. Okay, there will be some homeworks assigned, so make sure that you'll be able to access this volume 1. Okay, so what is anti-derivatives? Well, we know what a derivative is, and anti-derivative is just doing the opposite. It's kind of playing Jeopardy, right? You know the answer, the derivative, but you didn't know what the original question, what the original function was. Okay, so simple, of course, simple examples. If we have 2x, if this is the derivative, so I'm giving you the derivative, so the question is now, what is x squared, right? If I take the derivative of 3x squared, what is x cubed? Okay, the derivative of x cubed is 3x squared. Now, I can make it a little bit harder and not have a 3 there. What about x squared? Well, if I take x cubed, if I take the derivative of x cubed, I'm going to get, so the derivative gives me 3x squared, but I don't want the 3. So I'm going to compensate for that by dividing. So if I now do this, I get this quantity, right? If I take the derivative, because how do you take the derivative of this x cubed over 3? Quotient rule? Oh my God, no. These are constants. 3 is a constant. You just take it out. It's 1/3 times the derivative of x cubed, which is 3x squared. So what 3x squared divided by 3, that is x squared. That gives me exactly what I want. Okay? And we can do this now for any power. So I'm going to go rather quickly here. It is a review. So we have, if you have a power x to the m, okay, that's my m from mother. You see it has 3 bumps, and this is my n. Okay, I know everybody thinks that's an m, but look, what is that then, right? Okay, you have to get used to my writing sometimes. Okay, so x to the m. What's the antiderivative? Well, we see that when we take derivatives, we know that the exponent goes down by 1. So antideriving is doing the opposite. We have to add 1 to the exponent. But if I take derivative of this thing, I would get that exponent coming down, right? If you take derivative of x to the 5th, you get, if you take derivative, then you get 5x to the 4th. So we get this extra 5 here. We don't want that, so we compensate, we divide by it. Okay. Now this works for all m, not just positive m, also for negative m, even rational m, because that allows us to do square roots and so on. But there's one exception. Namely, m cannot be -1. Why is that? Well, try to plug it in this formula here. Try to do this here. What you get in the denominator? If m is -1, then -1 plus 1 is 0. And you pick command, the 11th commandment, thou shalt not divide by 0, right? So that it's clearly not possible. So what does that mean? X is -1. What is this? Well, this is 1 over x, right? It's another way of writing it. And we know what the antiderivative of 1 over x is. That's ln x. Okay? So this is what we call the power rule for integration. For antiderivatives. But that's why did I misspeak here? Because that's exactly what we're going to call it. Okay? Okay. Now there's one issue here that I should start from the beginning. I said it's Jeopardy, right? So here, let's look at my first answer here, 2x. And I said, oh, therefore the function is x squared, because if I take the derivative of x squared, I get 2x. True, but here's smartass. A smartass says, okay, I want this number, x squared plus 2034. Is that correct? Yeah, because if you take the derivative of this function here, the derivative of x squared is 2x, the derivative of the constant is 0. So in other words, you can always add a constant and still get the right answer. And so how the way that we denote this is by just saying you can put here any constant. So C stands for constant here, meaning any number that we want to put there. So therefore, in formulas, we should always write a plus C when we antiderive. Okay? Okay, there are, of course, other antiderivative rules. Just quickly, we have also the sum rule. I'm not going to give the formula. Let's just look at an example. Suppose you, sorry, I forgot one more rule, the sum rule and also the constant rule. Let me explain this one first, perhaps. Suppose I have to take 5 times x cubed dx. Oh, sorry. I haven't written. I'm writing down something you don't recognize. Right? What the hell is this? Okay. So let's introduce a notation. The notation for antiderivatives is, so the antiderivative of a function we write this as this. So okay, what does it mean? I'm gonna clean up my stuff here. So let me write this differently. If I take the antiderivative of x to the m, then this is given by that. The antiderivative of x minus 1, let me get rid of this dx here, is this. So we're using this single symbol here that we just introduced in the previous video, this integral sign, and we put here the function, the expression, whatever it is, and again the dx. Wait. That's why using this symbol for the same thing? Well, it's not exactly the same symbol. You know what? You see what is missing? There are no endpoints, and so this is called an indefinite integral. And the other one, when there are endpoints, is called a definite integral. I'll come back to that. So an indefinite integral is just a new word for antiderivative. Okay, and very often we understand that we just say integral instead of indefinite integral. Now, in video 3, I will explain why these two things look so similar and are almost called the same, but that's yet not there. So, okay. So what's the constant rule here? So here's an example of the constant rule. So this means, again, this symbol here, 5x cubed dx. So I'm talking about this one now, okay? This means that I have to find the antiderivative of 5x cubed, right? This is now what this symbol means. Now, the first thing you can do is always do this. This is what the constant rule says. You can bring the 5 out. And then we're dealing with this guy. And this follows in the category of power rule. So that is 5, and then add 1 to the exponent, divide by the exponent, plus c. Okay? That's the constant rule. What's the sum rule? Well, let me an example of the sum rule. Suppose you have to do now x to the 4th plus radical x dx. Okay? It says if you have a sum, you can take the derivative of the first and the derivative of the second and add them up. Because why are these rules true? Because they are also true for derivatives. So if it's true for derivatives, you can do it also for antiderivatives. Okay? All right, so x to the 4th, okay, I add 1 to the exponent, divide by it, because that's the power rule. Oh dear, radical x. I don't know. Oy. Radical x, what to do with radical x? Sorry, it sometimes freezes. Well, I just said, right? You can write radicals as exponents. So let's write that. What is the exponent here? Half, right? And then I told you this power rule works for any m as long as the m is not negative 1. So what we get here is x to the 5th over 5 plus, add 1 to the exponent, a half plus 1. I hope everybody agrees it's 3 halves divided by 3 halves plus a constant. Okay? And now we can combine this, right? So suppose we have to do this. 3x to the 5th plus 6x to the 4 over 4 plus 5 cube root of x squared. Don't panic, it looks way harder than it is. Because, first of all, what we're going to do is the sum rule. We can take, and I'm writing it out in detail. After a while, you're so used to that, you don't even do the details anymore, right? So, but here I'm going to do, right, so each of these I'm going to write as each term. I'm going to take the antiderivative, and then add them up. Now, the first thing that's the sum rule. The second thing is we have the constant rule. We have these constants 3, 6, and 5. I'm going to take them out. Okay? It's a video. I can do this, right? So I'm going to do this on my video here. I'm going to take this 3 out. That becomes 3 here. I'm going to take this 6 out. That becomes, well, 6. And I'm going to take the 5 out. That becomes 5. If you don't need where they come from, just scroll back a little bit. Good. This is the power rule, the first one. The second and the third one, I also powers, but I still have to write them as powers. Okay, so let's do this. 1 over x to the fourth. How do you write this as a power of x? Remember, if it's in the denominator, it becomes a negative exponent, right? So this 1 over x to the fourth is actually x to the negative 4. Agree with me? Okay. If you don't remember, go scroll back and look at it again. What about this guy? Everybody thinks with me, and everybody hopefully sees. Well, so this was what I had, right? This index is the denominator. This power is the numerator. That's where people get very often confused. So make sure that these go on the right spot. And it looks a little bit like the layout, the 3 is higher than the 2, right? But it's just the other way around. Don't think too, I mean, perhaps some people write it therefore like that. Okay? And you see a little bit better the relationship. But in any case, that's what it is. Now I can do my power rule. 3, that's just a constant. X to the fifth, I add 1 to the exponent, divide by that, plus 6 times. Add 1 to the exponent. Now be careful, minus 4 plus 1 is minus 3, right? Who do I divide by? Well, by set minus 3, plus 5. X 2/3, 2/3 plus 1, that's 3/3, that's 5/3. Divide by what? 5/3, plus C. So now you ask, Professor, do you have to simplify? Answer, do not simplify if it's not necessary. Why? Why do I ask this? Well, it's just, my heart also breaks, and I see everybody, you write it correctly, and then in simplification, the whole thing goes berserk. You make mistakes, and so I don't want you to simplify, because that way I also see what you're trying to do. Right? Now I can see that where these numbers come from. Once you simplify, I don't see this anymore. Do not simplify if not necessary. That's my motto. But sometimes it is necessary. Now, let me explain when it's necessary. One, it's necessary if you need to check your answer with a solution from the back of the book or where else, because often people like to simplify things and they will give you the simplified version. Another case where we need to simplify sometimes is because we need this antiderivative to do some more work, and then you need to kind of simplify things. I'm not going to do this here, and because that's algebra, and that's something that you should know how to do. I know that some of you still make mistakes with that, but so let's not do it. Okay, that's our antiderivatives. Let's look a little bit more at what else we have, because we did the power rule, we did the sum rule, the constant rule. Okay, well, not one. The product rule, right? Okay, so here the antiderivative of x cubed times x to the fifth dx. Okay, Professor, let me do that. I'm going to do it in red so that you see very well what I'm doing. I do add 1 to the exponent, divide by 4, and I do add 1 to the exponent, divide by it. That's my answer. Wow. Plus C. Otherwise, you're going to... Is that correct? Let's see. Well, this is, of course, also x to the 8th, right? And by the power rule, this would be x, add 1 to the exponent, divide by it. What is this? If I would work this out, this would come out to be x to the 10 divided by 4 times 6 is 24. Oh dear, that's not the same. Is that possible? No. There's only one antiderivative up to a constant. Which one is the right one? Well, it is clear that this cannot be wrong, right? Because that's really what it is. So this must be wrong, the other one. Why is that? No product rule. You say, but there's a product rule for derivatives. Yeah, but it is not that simple either. If you take derivative of a product, it's not just taking derivative of each and then multiply together. It's much more complicated. And we will come back to this rule of derivative of the product rule for derivatives, and we will see that it leads to a new integration technique, but that's for a few sessions later. So for now, there's no product rule. In other words, if you have a product, you have to expand the product, if possible, or find some other ways. We'll deal with other topics, with other ways later, but for now, this is the only thing we can do. So, to give an example where you have to be so very careful, suppose we have to do this, x squared plus 1 x cubed dx. How do you antiderive this? There is no product rule. No product rule. It's important to know the rules, but it's also important to know which are not rules. Okay? So what does this mean? I cannot just integrate each separately. What I have to do is multiply them out. So I have to multiply this out as x to the 5th plus x cubed dx. And now I can end the derive x to the 6th over 6 plus x to the 4th over 4. And don't forget the plus c. Okay? So that is sometimes, it's a very common mistake people make. Here is another one. X to the 3rd plus x 5 x to the 4th divided by x to the 7th, x to the 5th, sorry. Let me make this x to the 5th. Dx. Oh, the quotient rule. If there is no product rule, you really think there's a quotient rule for antiderivatives? No. Again, you cannot just take antiderivatives of top and antiderivatives of bottom and put them in a fraction. No, 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 no. So what do I have to do? Well, with fractions it's even harder, right? And there are only few fractions you can deal with. Luckily this is one. Namely, you carry out the division, meaning you divide each of the numerator terms, the terms in the numerator, by the denominator. So this would be what? X cubed divided by x to the 5th would be 1 over x squared. But I like to write it as a power. X to the power negative 2. Do you agree with that? Okay. And what's the next one? Again, whenever I ask questions and whenever it's things that you should, concrete examples, you should try yourself. Stop the video, try to figure out before I spoil the fun, okay? All right, so what's the next one? That is be 5 and then x to the power negative 1 dx. Okay, here we go. And the derivative x minus 1. I'm going to do the sum rule right away now. So the derivative of that, the first one is add 1 to the exponent, divide by it. And again, I know how to simplify this, but I'm not going to do it. Plus 5, that's the constant, takes out. And the derivative of x minus 1, add 1 to the exponent, divide by it. That's dividing by 0, right? Right, if I write this, I'm going to try to write it down. I'm doing it in red because it's wrong, right? Add 1 to the exponent, divide by it. That's not possible. What does that mean? There's no answer? No. Remember, this was the one exception. There was one exception in our power rule. That's exactly this power. And therefore, this was just ln x. Okay, you see that? All right, so very, very, very quickly, what's the antiderivative of sine x? Why a negative sign? If I take the derivative of cosine, I get negative sign. But I don't want negative sign, or positive sign, right? So that's how I have to compensate. Derivative of cosine x, think about it for a sec. That now is indeed sine x. Plus a constant. Okay. There are a couple of more that we know. The antiderivative of secant square x dx. That's tangent x, right? The antiderivative of secant, that's a different story, and we have to wait for much later. So, so many things we don't know yet what antiderivatives are. And in fact, this is part 1 of the course. The first 2 weeks, that's what we're going to concentrate on, finding these antiderivatives. All right, so that one we know. There are a couple others. So in other words, now you look at your tables of derivatives that you had in the volume 1, and these are also tables for antiderivatives if you read them backwards. Okay, just to give one example, what's the antiderivative of this guy? This might not, that might be a bit too long ago to remember, but the derivative, what is this a derivative of? This is actually a function that we know what the derivative is. That's namely the inverse trig function, arctangent. I know that the book and many calculators and many other people write this here, but this is a horrible notation because it looks like you take in the reciprocal. It's not reciprocal, it's the inverse. So I never use this. I always write arctangent, arcsecant, arcsine, and so on. Okay, there are more, and I'm going to leave that for you to look at the tables and the homeworks to find out what the others are. Now I want to, there's one important one, of course, ex dx. What's the antiderivative of that? Well, that's the nice one, right? It's equal to its own. It gets a little bit trickier if I take a different base. What's the antiderivative of this guy? Okay. We know that the derivative of 2 to the x, let's write down what the derivative of 2 to the x is. It's an exponential function, so we know it's equal to itself, 2 to the x, times some the logarithm of the ln of 2, the natural logarithm of the base. Why don't we see this in e? Because the natural logarithm of e, that if you take that as base, then that's just 1. ln of e is 1. That's why we don't see that number. But in general, it's there. Now, what's the antiderivative? Let's think about it. I don't want this, and if I don't want it, what do you need to do? Divide by it. Okay? So this is how you take antiderivatives. There's also something like, yeah, no, sorry. That's what I want to say. One last thing, and this is a little bit, let's look a little bit harder problems here. It's not harder, but let's think about this. Antiderivatives. Well, you would say e to 3x, right? The derivative of e, what is the derivative of e to 3x? Is that correct? Let's see. That's my first guess. But we have a chain rule thingy going on here, right? This is inside function. So we know the derivative is e, plug in the inside function, times the derivative of the inside function 3. Again, an extra factor that I don't want, just divide by it, divide it away. So can you figure out what this would be? Okay, the answer is, if I take the derivative of cosine 4x plus 2, first of all, it gets minus sign, so that's why I put the negative here already. But if I take the derivative of this, I'm going to also get what out? The derivative of the inside function. Is that 4 or 2? That's 4, right? So that's why I divide by 4 and not by 2. So these are this so-called compensation. So these are, we compensate here. We do this in any, wherever this is necessary. You see it happening here. You see it also, it actually also, it's the reason why we have this division here in the power rule, okay? But do not confuse the antiderivative of e to the x, for instance, or e to the dx. Some people think this way. They say, oh, it's the power rule. I know what it is. It is e. You add 1 to it and divide by it. That's the antiderivative. No. Is this the same form as this? No, because here x is the base and the power is a fixed number. This is exactly the opposite. This is what we call a polynomial or a monomial. What is this? This guy, the base is fixed, e here, and the power is actually the variable. So this is what we call an exponential function. So do not confuse those, okay? Each form has its own rules. Okay, there will be more homework problems with some other issues, little issues I haven't addressed yet. So that is antiderivatives. Now, next video will link them both together.